We looked at before the ratio test, now the root test. The root test examines convergence on a series. Um, the argument is the same as in the ratio test, but instead of using uh, the absolute value of the ratio, we use now the absolute value of the nth root. So we said that the series that's given converges absolutely when the limit is of the nth root of the absolute value of the sequence is less than 1. This series diverges if that limit is greater than 1 or infinity. The ratio test is inconclusive if this limit is equal to 1 directly. And if this test is inconclusive, that means you know nothing about the convergence or divergence of the series based on the test. You would then have to use another test. So let's apply the root test to this. So we take the limit as n goes to infinity, and this is the nth root of the absolute value of 1 over 5 to the n. This is equal to the limit as n goes to infinity. You can drop the absolute value sign because 1 over 5 to the n is positive as n goes across positive numbers. And so what we have is 1 over 5 to the n raised to the 1/nth power. So this is the limit as n goes infinity. 1 to the 1 over n is 1, and then 5 to the n raised to the 1 over n is 5. Looks like this 5 is about to fall off the boat. The limit of 1 over 5 is 1 over 5. It's less than 1. And so here, about the root test, the series is convergent. What about this one? When you have terms like this, basically what they're saying is, when do you know to use the root test? Well, if you have a series and if the power is the nth power, right? So use the nth root test. This is the limit as n goes to infinity of the nth root of the absolute value of 3n plus 2 over n plus 3. Come on. So this is the limit as n goes to infinity. Now what you have here is 3n plus 2 over n plus 3. This is to the nth raised to the 1 over n. So those powers, they cancel out. We have left the limit as n goes infinity of just 3n plus 2 over n plus 3. This limit directly here is equal to 3. it's greater than 1. Uh-oh. If the limit is greater than 1 or infinity, then the series diverges. So now we apply the root test to this series. So this is the limit as n goes to infinity of the nth root of the absolute value of -1 to the n all over the natural log of n raised to the nth power. So this is the limit as n goes to infinity. Now the absolute value of -1 to the n is equal to 1, and this is divided by, this is the natural log of n raised to the nth power raised to the 1/nth power, so all we have left is just the natural log of n. Now 1 over the natural log of n as n goes to infinity is equal to 0. So the series converges absolutely by the root test. What about this one? So the limit as n goes to infinity of the nth root of 1 over n minus 1 over n squared. This is raised to the nth power. Notice that just gets rid of the nth power for us because this is 1 over n, the 1 over nth power there. So this is the limit as n goes to infinity of 1 over, don't even ask me what that was. It's probably that write-in that I saw on Star Trek, right? But no, 1 over n minus 1 over n squared. The limit of 1 over n as n goes to infinity is 0, and the limit of 1 over n squared as n goes to infinity is 0. So we have 0. It fits the description of the test, and so we said that here the series converges absolutely by the root test. Let's look at some more. Now, for the rest of these problems here, 51 and 68, determine the convergence or divergence of the series using any appropriate test from this chapter. So we're not limited to the ratio or the root test. You may be able to apply the direct comparison or the limit comparison, a p-series, the nth test for divergence, geometric series, partial sums, that is, use the telescoping method, the integral test. So we have a lot at our disposal in terms of what you can use to be able to determine the convergence or divergence for a particular series, and also the alternating series test. Right? That's interesting. We apply that one. So this series converges by the alternating series test. If you take the absolute value of the sequence values, the series becomes harmonic, so it's divergent in that regard. But this series in and of itself is convergent, conditionally convergent. You remember that test said 1, look at the limit of the sequence, 5 over n. You want the limit to equal 0. Then 2, 5 over n is decreasing. For n, for natural numbers of n, that and n increasing. What about this one? So I did say that this guy is convergence. Yep. If you rewrite this, this is the summation as n goes from 1 to infinity. This is 3 all over n to the 1/2 plus 1 is n to the 3/2. So this is p-series convergent. You remember with the p-series that if p is greater than 1, then we have convergence. What about this one? This one diverges by the nth term test for divergence. Let's apply that. Notice the limit as n goes to infinity of 5n over 2n minus 1 is equal to 5 over 2. Right? It's not equal to 0. The nth term test for divergence said that if the limit of the sequence is not equal to 0, that implies that the series diverges. So what about this next one? Interesting. I think if we can rewrite this, we may be able to see what's happening. This is the summation as n goes from 1 to infinity, that negative 1 to the n, and then this is 3 to the n times 3 to the negative 2. This is all over 2 to the n. So that 3 to the negative 2 is 1 over 9. And write that in front of the summation. Doesn't hurt it. And this is 3 over 2 to the nth power. Two things that I apply. I apply in terms of the geometric series. We can apply that here, and as a matter of fact, if you want, you can plug in that negative here with that n. Just do that and make it easier. Because if not that, you'd have to apply the geometric series and the alternating series test. So here we just apply one. So this is negative 3 over 2. They're both raised to the nth power, so just write it as one term. Right. You know we have the geometric series test that looks at the ratio. Right? Here the ratio R is equal to negative 3 over 2. Right? This ratio has to be between 0 and 1, the absolute value of it. So the absolute value of R is equal to 0 over 2. For a geometric series to be convergent, zero has to be less than or equal to the absolute value of R less than 1. Otherwise, the series is divergent. Okay, so it's divergent. Well, let's look at this next one. This is the summation of 10n plus 3 divided by n times 2 over n. Looks like we can probably do a limit comparison. What I'm thinking in my head is how to get rid of that 2 to the n, because it throws everything off. It's not even comparable to 10 times n, the 3, and the n. So we can remove it by comparing it to the series of 2 over n. So compare it to the summation as n goes from 1 to infinity of 1 over 2 to the n. So this guy is a known convergent series. What kind of series? It's geometric, right? Okay. So if that's the case, we do the comparison. So this is the limit as n goes to infinity. Here we have 10n plus 3 over n times 2 to the n divided by 1 over 2 to the n. This is the limit as n goes to infinity of 10n plus 3 times that 2 to the n. And this is all over n times 2 to the n. Well, the 2 to the n's cancel. So we have now the limit as n goes to infinity of 10n plus 3 all over n, which this limit here is equal to 10. The conclusion for the limit comparison test is that you want the limit to be finite and positive, which it is. Of which L equals to 10 is finite and positive. This implies that whatever happens to 1, to the known series, also happens to the series in question. So this implies that the series converges also. Okay, we do a direct comparison here. With 1 over the series 1 over 3 to the n. So this is geometric series convergent. Okay. Now, notice that -1 less than or equal to cosine n less than or equal to 1. And 3 over n positive for all n. That's a natural number. So this implies that -1 over 3 to the n less than or equal to cosine n over 3 to the n less than or equal to 1 over 3 to the n. Well, since the summation as n goes from 1 to infinity of 1 over 3 to the n converges, then here by the direct comparison test, the series, the summation as n goes from 1 to infinity of cosine n over 3 to the n also converges. Notice that the sequence 1 over 3 to the n is larger than cosine n over 3 to the n. You know that the end result of this guy, its series, converges. So whatever happens before that must also converge. And then the last one, let's use here the ratio test. I'm thinking ratio test because I have this n factorial, but then I have this number raised to an nth power. So, and then the -1 to the n with the ratio test makes use of the absolute value, so that goes away as well. So we apply the ratio test. So we have the limit as n goes to infinity of the absolute value of the n plus 1 term divided by the nth term. So this is -1 to the n plus 1 times 3 to the n plus 1 minus 1 is 3 to the n. That's divided by n plus 1 factorial. This is all over the original sequence. So those negatives will go out, then we can drop the absolute value sign. So we have the limit as n goes to infinity of 3 to the n here, and this is times n factorial that came from downstairs. That's divided by, this n plus 1 factorial is n plus 1 times n factorial, right? And this is times 3 to the n times 3 to the -1. So the 3 to the n's cancel, the n factorials cancel. So that leaves us with the limit as n goes to infinity of 1, well, it really becomes a 3 upstairs. This is 3 to the -1, so 3 all over n plus 1. And as n goes to infinity, 3 over n plus 1 goes to 0. Now, by the so-called ratio test, that test said that we have convergence here if this number, the limit, is less than 1. We get 0. That works. So by the ratio test, the series converges. There's so many various tests for these sections, and so you can see now why it's obvious that I allow you to use that sheet that has all of the ratio tests, all of the series tests on it. I think as just a goal in mind when you're trying to apply what test works is to, I think the easiest one is the nth term test. I'll try that one first and see if I can get divergence by taking the limit of the sequence. If it's not equal to 0, then that helps you with divergence for the series. And then from there, if the nth term test doesn't work, some easy things to look at is, one, the nth term test. If that doesn't work, then I think, is it geometric? I asked that question. If it's geometric, I apply that. Can I compare it to another easier but comparable series? Then I either, in my head, I'm thinking direct or limit comparison. I think the so-called ratio, the root test, obviously, if it's a ratio, um, and if the terms have like n terms in them and then powers of n, definitely ratio test. If there's an nth root, the root test, obviously. Um, I try to avoid the integral test. Oh yeah, going back to the first step, if it's if I can apply the nth term test. If not, then I try to go to the p-series and then the geometric series. If they work, then fine, you can just look at those directly. If not, then you go to the comparisons, like the limit comparison, direct comparison, and then more rigor, the ratio test or the root test. If it's alternating series, that's easy. If it's alternating series, you have a -1 to the n, then you want to check the limit to make sure the limit of the sequence goes to 0, and then make sure that those sequence values are decreasing. And typically that should happen, but we've seen a case where that was not the case. One worked, but the other one didn't. Well, hopefully with that in mind, you should do well. Go well, stay well.